Sveiki! Tā, 4 minūtes līdz lekcija.
Okay. Es tikko bišķi nodarbojos ar visu to, ko es visu laiku darētu. Ar datoriem, monitoriem, krāsnē, savādi kārtībā.
Labi, tā ir nedēļa. Bišķiņ patērīsim, tā ir. Pie jūsu.
Nu jā. Nē, nu tāds.
Būs ko.
Taisīsim tauku.
Dzīve.
Tu pēc 7 minūtēm ies ēterā, ja?
Jā, es būtību mikrofons jau skarādu. Es skatos uz smūtiem kondensātu.
Jā.
Būs par kam stāst. Karpiņas, tādas, vien tādu es tumbiņu pārtais.
minus. Let's start. I have a big plan for today. To start talking about limitation of digital signal processing. But before, I need one, how to say, supplementary idea, auxiliary idea. I'll need one term. So I'll explain it first, and then we can continue. Chalk disappearing. Let's see, came already broken. Oh, it's a cheap substitute. Near the same, but it's different brand and appears to be a cheap substitute. Okay, let's start with one idea. Let's say I have a signal, delta from time, being like this, minus tau by half around 0, and its magnitude is 1 by tau. Such rectangular pulse. If we compute area of this pulse, its area will be from minus tau by half to tau by half of in time equals to integrating tau by half to tau by half 1 against tau the time brings us 1. So area of this figure is unity. 1 well, okay. Now let's think about a bit differently. I have some signal in time, and I have my here, let's say this is t0, and in red I have del time minus 0. Offset. I have my rectangular pulse with offset. I'm interested in one value. Say g integrate from minus infinity to infinity. Del that 0 this time equals to, what will I get? What will I get if I perform an integration on the product? Tau by half is 0 plus tau by half S not there. also in time. For any signal, it's possible to select tau small enough. I can have tau so small, what? S t minus tau by half should be approximately equal to plus tau by half. I can set this time, time range or time gap small enough, so signal on both sides will be approximately equal. This allows me to rewrite my approximately signal value at a middle point, integrating t0 minus tau by half, t0 plus tau by half, delta, and equals this one equals to 1, so it will be my signal value at a t0 point. Once more, integrate from minus infinity to infinity. Delta t minus t0 t time approximately equals to signal value at t0. Since this is true for any time moment when we have our signal. So this is true for any moment. In general, I can select 0 everywhere from minus infinity to infinity. So I can use time instead of t0. I can do this thing. I can write. Why I'm writing? I mean, can be integrate from minus infinity to infinity. No, this is wrong. No, this will not work. This will work as x delta x dx. Yeah, I'm using additional variable x here is simple. How to say supplementary variable or additional variable I need to integrate somewhere. Also interesting, what I can rewrite my integral in opposite minus x. The x, there is no difference, go this way or this way. What do I see here? Do you see something? Some stupid formula. Unclear. What physical meaning of this formula? Physical meaning. I don't know, but like this. This is my original signal. I don't know, maybe it's voice recording. It's voice. It's not a recording, it's a voice as it is. I can represent it as a sum. These are deltas. You understand? I can substitute my original signal with the sum of small rectangles. My signal can be represented as a sum of, do you see, multiplication with delta. If here is a t0, it's like cutting a slice of my signal, one small slice. This formula that I just erased tells me what I can substitute my original, I don't know, maybe it was a voice, with the sum of such slices. Why I'm interested in such slices? Let's make it 100% clear. At this moment, weight of slice is something. Okay, I told it's small enough we have time of slicing small enough, so signal of t minus tau by half is approximately equal to signal plus tau by half. Approximately. When it will be true, not approximately, but true. When tau will go to 0. If I have infinite thin slice, this is true absolutely. Because slice is ideal thin. What I'm doing, I'm introducing the fastest possible thing in this world. Delta function. It's a limit when tau goes to 0 of my rectangular cutter. Maybe it's not enough space, so here is the 0, and this is delta t minus t0. Infinitely thin. It's a thinnest thing possible in this world. It's absolutely thin, and it's the fastest thing possible in this world. It's an ultimate limit for fastness. Because where we started, a magnitude of original minus tau by half. Tau by half. What was the magnitude? 1 against tau. What's the magnitude of delta function? If tau goes to 0, it flies up to sky, up to infinity. It's like an absolutely thin needle pointed to infinity. delta function. So, delta function of time equals to infinity when time is 0 and 0 when time is not 0. Delta function is 0 equals to 0 when time is not t0 and infinity when time is t0. Absolutely thin. Needle goes up there. Okay. Also, we still have our integral. So integrate it minus infinity to infinity equals to 1. And infinity to infinity is not that. Delta T0 equals to signal at point T0. Also, I can substitute my signal with minus infinity to infinity. Sorry, S not x. Delta x minus time dx or in infinite S not x delta time minus x dx. What's the meaning of these two white formulas? What do you see? For example, this one. You see any physical meaning? Anything? White formula, useless, no? Another white formula. Okay. White formula in green. Cloud. Time. Signal as time. 1 tau, 2 tau, blah. Table of values. Number S no I tau. Value. 1, 2, 3, blah, I don't know. 3, 5, 2 volts. What is depicted in orange color? Discrete values. This is original continuous signal. Yeah. Orange point is point value. One value, one sample, one record in your digital system's memory. Yeah? When you digitalize something, I don't know, it's sound, video, anything, name it, you will have a table of values. Yeah? Okay? You will have table of values. One value is one sample. 10 sample is used. Yeah? Measuring one is taking a sample. Some array of samples, for example, for one period, is a set. Do you feel meaning of these white formulas? Well, ideal sampling. Moment when white continuous line became an orange dot, a point in computer memory, is a sampling. So ideal sampling device, real analog to digital converter. Do you know what mean this term? Analog to digital converter. ADC. Okay, analog. This IC is an ADC, this one. It has one input for voltage, output for data, and input for control. What it do? Analog to digital. Analog to digital converter. You supply it with analog signal and command do, and it will give you out value of this voltage. It's like automatic voltmeter, which gives you out a digital value of the input. Then this processor will work with it. Analog to digital converter. Microprocessor that will process this data. Take it as sample, it's like, it's analog to digital conversion. Moment when continuous signal become discrete. Your digital signal processing system needs to perform analog to digital converter. It's taking a set of samples. Measure at this time, at this time, at this time, and this time. Take measurements. So what formula I wrote is ideal ADC. This difference between real ADC and ideal is infinitely fast. Real is not absolutely fast, but you can use one thing. It's a sample and hold. All time devices had it as external. It's additional circuit. Modern ADC ACs had it inside. Sample and hold freezes value when you send command do measurement. Sample and hold circuit at this moment, freezes signal value to this point, and then conversion, measurement occurs. Okay? Small remarks on delta function. So multiplying signal with delta function, it's like taking a sample of it. Perform measurement. Okay. Also, a couple notes. So 0 delta t. The t equals to integral from 0 to infinity dt and equals to 1/2. So if we perform an integration from minus infinity to time of delta function, take minus is 0, the time we will get 0 until we reach our t0, 1/2 when will be equal to t0, and 1 if t greater than t0. This clearly shows us what delta function can be assumed as a derivative of switch on function. Ideal switch on occurs infinitely fast. Magnitude 1, 0 time 1 as a function of time. It assumes what? How to say? This point goes into this point infinitely fast. At this point, there is in real life it would be a slope. At this point, there is no slope for ideal function. And if it goes infinitely fast, derivative of it will be infinite. Okay. Next moment about delta function. It's
Professor,
yeah.
let me ask you something to figure out this. Is this delta function just ordinary time function, or it is like it's in Laplace domain, like there's a delta plus?
At this moment, it's a time function. Only one tiny moment. It's a fastest possible time function. It's a ultimate limit of fastness for all possible time function. Now let's speak in frequency domain. Yeah, 1 second. I will take a look in frequency domain. What it is in frequency domain? In time domain, it's ultima fast, like a needle. Ideal, absolutely thin line going up infinity. Kind of in drawing, it's array. Array absolutely thin, starting from 0 line, goes up to infinity, and it's absolutely thin. Now, what it will be in frequency space? Yes, what we will get if we perform Fourier transform on it. If we would try to obtain spectral function for it, we will need to integrate in infinity space T0 f power omega t dt. That's what we need to do.
Is not it plus I imaginary e power to is not
Minus your
like,
minus. If you perform Fourier transform, it's minus.
no, like for forward Fourier transform, I think it's minus, but for backward,
I am performing forward, I need spectral function. I'm trying to get and what will I get? J omega T0. In case I have it and 0, spectral function of my delta function will be 1. Delta function in 0 point, at point 0 time, has absolutely uniform spectrum. Unity in all frequencies. Remember my demo on non-periodic signals. The faster changes, the wider will be spectrum. Yeah?
In frequency.
Yeah. This thing changes are absolutely fast. Nothing changes faster. And it has absolutely uniform and absolutely infinite spectrum. It occupies all frequencies. If you have something changing absolutely fast, it will take all possible frequencies. It will have unity, value of unity, on any frequency. It occupies all spectrum from beginning to the end. The slower thing, if something changes slow, it has small, limited spectrum. If something changes fast, it occupies more and more frequencies. This thing is absolutely fast. And it will take all frequencies. If it would exist, it will kill all communication because it will occupy all possible frequencies for broadcasting, for communication, everything. Okay, I can also perform inverse Fourier transform. I can get my delta function as 1 divided by double P minus infinity to infinity. It's omega. Yeah, but here I'm writing inverse Fourier transform and case plus. What will I get? 1 divided by double P means infinity to, sorry, it's mistake, here is delta omega. F power J omega, the omega. This can be useful. Now one small moment. Let's say I have something like maximum cosine omega 0 time plus phi 0. I have harmonic voltage. Spectral function of it will be what I need to write. I get from minus infinity to infinity. Cosine omega 0 time plus phi 0 a power minus J omega time theta. Yeah. If I would like to perform Fourier transform, I need to deal with this. Now, with the help of Euler's Pythagoras formula, I can rewrite my object as O max divided by half, integrating from minus infinity to infinity, a power j omega 0 time plus phi 0 plus a power j omega 0 time, and here should be, I'm always afraid, and this should be multiplied by a power j omega time, and I'm integrating in time. Now what? Now I can do a trick. If there is a delta function of time, why cannot exist delta function of frequency? Delta function of frequency, I can write it using this integral form, a power j omega x dx. What I wrote? What is delta function of frequency? Infinity thin spectral line. Remember school physics? Device should be somewhere. Oh, here it is. Something familiar? Oops. It's from your physics.
Yeah, like
Glass prism.
light changes
Yeah.
its direction. Yeah.
Light spreads in two spectra. You need to, here you're observing it, and here is a glass prism to break light into spectra. If you observe something like, I don't know, natrium or hydrogen, you have these spectral lines. You should. Infinitely thin spectral line. This light integral is in the spectral line, infinitely thin. Strange. It's white, but it may be yellow. What I'm writing? So I need to note what 1 divided by double t is minus infinity to infinity. A power j omega 0 plus minus. No. I need to be correct. Omega plus minus omega 0. Yes. X, the x should produce me a delta function of omega plus minus omega 0. So, for my voltage, spectral function can be written as P U maximalize or max F power j V0 delta function of omega minus omega 0 plus F power minus j V0 delta function, make no mistake, omega plus omega 0. What does this mean? If I have something like cosine of omega 0, it can be represented with two omega 0 it will be omega minus omega 0. Okay, simple. This one will be at omega 0 and this one at minus omega 0. You will have two spectral lines, two symmetrical spectral lines. If you have only one frequency in your signal, it will be represented with two symmetrical, or if you take real part 1, is 0 frequency. It's normal. What we know about spectrum? If it is only one frequency, spectrum should contain only one line. Ideal. So spectrum of ideal signal is ideal thin spectral line. Hey you. I will kill this TV set one day. 1 second, I'll be back. You see what I'm doing? I'm preparing space for large formula. Here, what I get? This generator gives a very pure harmonic signal. It can be in lower frequency. It can have, it's so pure. What harmonics are less than 1 in 10,000. Now, need to be higher frequency. It's limited with 1 in 1,000. So harmonics, higher harmonics level, it is less than 1 in 1,000. It gives me a very pure harmonic signal. It's designed for high quality acoustic testing. Yellow line is signal. Red line is discrete time Fourier transform. What should be? Knowing what I just wrote. If this is, actually it's, it's not, is it real 10 kilohertz? Yes, it's a 10 kilohertz. It's very good 10 kilohertz. Should be 10 kilohertz. Very pure. What should I see?
To get 1,
At red line. Why 1?
like you mean?
This one has only one harmonic component, 10 kilohertz. What should I see? Delta function, ideally thin line at 10 kilohertz.
Yeah, which is
Red, in ideal case, I can shift someone. In ideal case, this red line should be infinitely thin. With the magnitude of signal 10, it should be 3 multiplied by square root of, now it's in RMS, but if in magnitude it should be or 3 volts or 3 multiplied by square root of 2, depending what we're showing, magnitude or effective values. Should be infinity thin, and it's not. Okay, we will look on it. But first, I need to write some formulas. Let's assume I have a pulse sequence. I perform a Fourier transform of a pulse sequence. Infinity to infinity. What will I get? I will get sum. It starts from minus infinity to infinity. Double P divided by time. Here. A wide frequency. I can immediately use values of spectral function, delta function, omega plus k double P divided by period. What meaning of this formula? Here, omegas is Fourier transformation result of original pulse. Remember my sequence of non-periodic pulses.
Yeah, you mean like circuit with capacitor? And
Yeah, energized from pulse generator.
yeah.
What do we saw? Lines, 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 lines
Yes, like this.
in spectrum.
Like infinite damage.
Yeah. This thing now tells us what sequence of pulse will be represented with discrete spectrum. Actually, see this part? It's a spectrum of pulse at a discrete frequency. One pulse has uninterrupted spectrum. Sequence of pulses will have discrete spectrum at a frequency line double p, k double p divided by time. If you would like a trick, 1 second. For example, I perform Fourier transform on sum where m change from minus infinity to infinity, delta function t plus m t. Time. Pum, pum, pum. Ideal. Lines spaced with a period t capital. If you perform Fourier transform on this, spectrum for each line is unity, all frequencies. Here you will get double p divided by period, sum like from minus infinity to infinity, delta function of omega plus double p divided by time. You will get set of ideal vertical spectral lines. One remark on another way to create sequence, minus infinity to infinity, and time delta function t plus m time will yield 1 against time. Spectral function, it should be for my signal, for my original pulse, omega plus k double p divided by period. Again, nice discrete spectrum. I have time. Now I would like to show something. Here is my okay, here is my setup. I have generator for 10 kilohertz. It's very pure 10 kilohertz signal. And two scopes. One digital, one analog. Here is my old analog scope. They show same thing, yeah? Yeah. I'm changing scale. Oh, something with low resolution. Something interesting, but I can go forward. I would like to go forward. Look at this. What my scope is showing? What this is signal with frequency 2 Hz. And what in digital space? Where is spectral line? Where are you? Spectral line? Oh, possible here. Just need. Okay, where is my spectral line? Oh, here it is. Just need to. Here it is. Where is my cursor? Bring selected cursors to the center of screen. So what's the frequency of this? Oh no, 2.5 Hertz. Oh, 1 second, here. 3 Hertz. Wait 1 second. Did signal changed? It's the same. But why we are looking at something here? 6 Hertz. $25 Hertz. Wait 1 second. It's still 10 kilohertz signal. Here, nothing changed. My generator still produces 10 kilohertz. But for digital scope, my signal now appears to be a 25 Hz signal. What's going on? It's a bit adjustment.
Is there any frequency filter?
No. No filters. See, nice. Near steady signal. I'm so... Oh. 6 Hertz. Indifferent. Yeah. And 1 second. I can go in different time scale. Oh no, it's 10 kilohertz. It's really 10 kilohertz. But if I compress,
It's because of you zoomed out the time.
I'm compressed time scale, and I get this strange behavior, 6 Hertz. No super slow signal. 1/3 of hertz, 0.35. Nice signal. In reality, it's still 10 kilohertz signal. You can say analog scope do not change. Shows absolutely no. (400 millihertz). It's still 10 kilohertz signal, but we do see 400 millihertz. Funny, isn't it? Something strange here. Exorcist should be called. Nice harmonic signal, only at very strange frequency. 442 millihertz. How can it be possible? I delivered to very good generator. We have this nice, steady, sliding signal. What's this? An effect called aliasing. Overlapping, but good name for it, aliasing. It's one of the basic limitation of digital signal processing. What's going on? Why we do see something very strange here?
As I know about aliasing, like after certain frequency, if frequency increases after certain frequency, it decreases.
In the easy approach, what's going on? I have a harmonic signal, let's say cosine omega. In good case, I perform something like this. It's okay. I will get something close to my signal. This would be a limit case with sampling time equals 1/2 of my signal period. So I have here cosine double T. Here is a border case. I have 2 sampling per period. Still possible to understand something. But what if I increase sampling period? If I increase sampling period, I will get first sample here, next sample, for example, here, one, two, 1, 2. Next sample will be here. Something absolutely different. Here, I'm in the situation where T is greater than period. I have some kind of stroboscopic effect. That's what's going on. I shrink time space, so sampling scope has a fixed number of points per its observation window. I shrunk observation window, and sampling points are falling to create kind of harmonic signal, but it's really stroboscopic effect. It shows some very strange near zero frequency. Problem of aliasing. Actually, Nyquist was first to point finger at this problem. And Nyquist, Nyquist told simple thing. What? If my signal contains harmonic up to omega, I need sampling being less or equal than T divided by K. Or F sampling should be at last twice F max. To get 2 points per period for highest harmonics, I need sampling frequency being at last 2 times higher or greater than the maximum frequency of my signal. Unlucky digital processing board. This part. Capacitors, resistors. Low pass filters. To prevent distortion from aliasing. This is ground. Multiplex. ADC. Anti-aliasing or anti Nyquist circuits should be added. They are LPF filters to cut frequencies above, cut components above Nyquist frequency. Or you will get this. It's a clear example of kind of stroboscopic effect or aliasing. Nyquist idea. But sampling frequency should be at last twice.
If time sampling is constant, is constant, I think my opinion that I told is not wrong actually. Actually I forgot to say if time constant is constant. Like if you increase frequency after Nyquist frequency,
you will get distorted signal. If you if your signal frequency is above Nyquist frequency or above double sampling frequency, you will get fake signal at
exactly.
different
fake signal.
This is fake. This is not true. This is I provoked error select I artificial decreased Nyquist frequency. So this one is fake. It's a slow slide. It is hard to get it with if you have, let's say, not so pure signal, you will get simple some kind of distortion. I took very good generator, so we can observe nice slide. It's a points for multiple signs. Yeah, it's always a track. You need, see, Nyquist frequency sets for you a performance margin. Your system should be, if you would like, for example, process sound with frequencies up to 20 kilohertz, you need to perform sampling at last 40 kilohertz. It sets a benchmark for your system's performance. CD quality 44 kilohertz. This 4 is a timed safety margin.
Professor, is it possible to observe, like, for example, non-harmonic any signal if we increase time?
Non-harmonic.
Like, increase.
Wait, which time we increase?
Like time. How do you call it? I forgot. Time. Like.
Well, it's a time space between samples.
Yeah, sample exactly.
All right.
If we increase time sampling for very high frequency, is it possible to see, for example, just a line or non-harmonic signal? Is it possible? Or?
So to get more precise, we need higher frequency, shorter space between measurement points.
Yes.
If we increase it, this means what will lower Nyquist frequency. And we will get our harmonics at some very strange. Actually, we will see some kind of stroboscopic effects, but which harmonic will be distorted which way, honestly, I can't predict. It can be very curious when bass, lower harmonics, remain under Nyquist frequency and remain undistorted, while higher harmonics are distorted. Let's try. Actually, I can try. I can try. How can I obtain first? I need kind of one moment. I will we can get. Okay, I have signal of 10 kilohertz, not so pure. Let's see how it will tiny shift. See, it's not so stable. I think okay, I got fake signal of 5 Hz. At this moment, I have pure, not super pure, but something like sine. Let's see what happens if I add third harmonic. Can I get it? Here it is with the third harmonic added. Can I add fifth harmonic now? 1/2 here. I should get something close to a rectangular signal. See, I have my rectangular signal, but on a very strange spectrum. Looks okay. 100 of first harmonic, first, third, fifth. But what about frequencies? Sorry, I need to go here. 4 Hz, 16, and 29. Where the base frequencies? Base frequency approximately 6 Hz. This one should be approximately 18. Something approximately close. So here is answer to your question. We see the same spectrum as original.
What about like without adding any other harmonic? Only in one harmonic. Can we see not harmonic signal? Let me draw my question on board. I wanna show you something.
Here is only base frequency. Okay. Without higher harmonics. Above Nyquist figures, okay, I reduce them, I can reduce them to 0. Harmonics reduced to 0, one frequency, but far above Nyquist. With addition of higher harmonics. We see our signal spectrum, but on ridiculously low frequency. Signal is something close to real. This one is real at 10 kilohertz, and this is fake at 6 hertz. Okay. If you need proof of this, ask Google for Kotelnikov's rose. I will know. I will not spend time. Here is Nyquist frequency limits higher. Actual, how to say, performance of your system limits frequency range you can process. Or frequency range you would like to process sets for you performance, how fast should be your system.